So in this video we're going to be looking at histograms. In the previous video we looked at bar charts. So I want to start off by looking at the difference between a bar chart and a histogram and when we would choose to use one and the other. So a histogram is really just a bar chart for numerical data, exactly the same. And the main difference between a histogram and a bar chart is that we separate the bars in a bar chart so they don't join on to each other, whereas they sit adjacent to each other in a histogram. And the question there is, well, why do we think this is the case? So, for example, on the left here, I've got a bar chart showing, pet preferences, and on the right, we've got a histogram showing the mass in kilograms of something, who knows. So we've got a bar chart for categorical data and a histogram for continuous numerical data. And the key thing here is, again, it comes down to order in some ways, that there's no implied order, and by joining them up we get a much better sense of the shape, or it grows and then it gets shorter, whereas here the shape is meaningless because we can order those bars in any order. So we kind of separate out the bars to tempt you less to be looking at what's actually happening in terms of the shape of the distribution. Also, it's to do with the fact that there's no there's no value in between dog and cat. There's no, they're just separate things, so their bars just need to be separate. Whereas here, there's implied order that means it's important that they go in order. But I guess the distinction I'm trying to make there is, even if this was ordinal data, we still wouldn't join them up. So even if there was an order, okay, there would be an order to the bars, but you can't be, so let's say this is, strongly disagree, and this is disagree. You can't be somewhere in between those two things. So we draw those bars quite separately to indicate that it's not actually possible to be in between those two things. Okay. There's a bit of ambiguity about discrete numerical data, and it can go both ways. So discrete numerical data can be represented using either a bar chart or a histogram. Okay, so you can join the bars or choose not to join the bars. That's purely just a preference in terms of what you're trying to indicate. These little charts here also show us a feature that we haven't discussed yet. We've got this little sort of heartbeat thing here, and what that's indicating is between here and here, that distance represents 5 kilograms, but from here to here, that's 30 kilograms. So we've condensed the x-axis there. We've essentially taken the x-axis that should have been this long, and we've folded it up, we concertinaed it, so that it's now only going to be this long, and then we're just going to start our scale from here. And we would use that if it's always going to be 0 at the origin. Some places you'll see they'll just start with 30 right here, but I think the origin should always be 0, so that is the point where the two axes cross. That should always be 0, and so if you want to start at 30, you do the little heartbeat and then you start your plot from there and call that 30. Okay. What else did I want to say here? I think that's probably sufficient. So generally speaking, a bar chart would be used for discrete numerical data, but the main exception, so I said we can use either, but we would usually use the bar chart. The main exception, however, is when we have a large volume of discrete data, and or when the data spans a really wide range of values. And in these cases, it becomes necessary to group the data. And when we do that, we create a histogram. So, for example, if we consider this data set, which I've got listed there, and I've got a bar chart drawn. Okay. Now, this is a really meaningless bar chart that all it tells us is the data's pretty spread out from 1 to 82. There's only, there's only one of each. All this bar chart is essentially doing is just listing the data again. It's just telling me 82's in the data set, and 77's in the data set, and 71 and 68. That's really all it's doing. It's not giving me any sense of kind of shape or anything. So we would probably group the data here so that we get some sense of what's happening. So here you can see I've now grouped the data. So the first bar represents, what's the data about? Sorry, I missed that. The age of guests at a family Christmas gathering. Okay. So I've grouped them into those aged between 0 and 10, those aged between 10 and 20, 20 and 30, 30 and 40, etc. So we can now see a bit more clearly that, the vast majority of those at the gathering were children aged between 0 and 10. and the second most frequent group is those aged between 30 and 40, who are probably the parents of those children aged between 0 and 10. Not all of them, but quite possibly. And so, you know, you can see the data is, this plot tells you a bit more immediately about the data than what this one does. Okay, this one here, you may as well have just looked at the list of numbers. I mean, it does tell you that it's quite spread out data, but that's probably all. So when we're grouping data, if we have continuous data, we have to group it, or if we have a large amount of discrete data, we group the data into what we call class intervals, or sometimes they're called bins. Your CADS uses the phrase bins, or the term bins. There's no clear-cut rule for determining the number of class intervals or bins that you're going to divide into. So, for example, you can see here that with this data set, I chose to divide it into 10-year intervals, which meant I had 1, 2, 3, 4, 5, 6, 7, 8, 9, maybe 10 if someone had been in that group. Intervals. Possibly it might have made sense to actually group this even further. It might have shown me a bit more, grouped them into, 15 or 20 year groups. But then I think if you went with 20 years, I think there would have been 2 combined and it wouldn't have told you anything. So there's a fine line, and that's where you've got to kind of make a bit of a decision there. So whilst there's no clear-cut rules, and hence there's no clear-cut rule about the number of intervals nor the width of each interval, it's generally agreed that we should end up with somewhere between 5 and 10 intervals. Any more than 10 intervals and you've probably got your data too spread out. Any fewer than 5, it's going to be too grouped together and not really tell you anything. It's really important that the data must be divided into intervals of equal width. Okay, so it would have, it's not okay to sort of have one group that goes from 0 to 4 and the next group that goes from 4 to 10, and then we go from 10 to 20, and then we go from 20 to 30. Again, it misleads you in terms of what's actually happening with the data if you've got different sized interval widths. And yeah, so equal interval widths, at least somewhere between 5 and 10 intervals. So you decide how wide your intervals should be based on that. So as I said, in the previous example we had 9 intervals or bins, each of width 10, and the grouped frequency table for the data would be here. So 0 to 9 is 6, there are 6 people, 10 to 19 there was 1 person, 20 to 29 there was 1 person, 30 to 39 there was 3 people. Generally speaking, so on the plot you'll see we didn't write, even though this was 10 to 19, it doesn't say 19 here and then 20 here. We understand that when we write 20, that's the beginning of the next category. So anyone aged 20 is in this bar here. Anyone aged 60 is in this bar here. Okay? So that's the convention around that. Note that while the intervals might be read on the histogram, so that's what I've just talked about, 0 to 10, 10 to 20, actually it means 0 to, in this case, 9 because it's discrete data. If it was continuous data, it would mean 0 to 9.99999. Everything would be in that first category. 10 would be the start of the new category, and then everything up to but not including 20 would be in that category, etc. If this was continuous data, it wouldn't be sufficient to round the interval to 30 to 39. So if we had intervals of 30 to 39 and 40 to 49 in continuous data, any measurement that's between 39 and 40, 39.2 for example, doesn't have anywhere to go. So actually the best way to write it is to use an inequality and say that the age has to be bigger than or equal to 30 but less than 40. Further Maths is a bit flexible and there's different notations depending on the textbooks you use. Sometimes you might just say 10 up to and 20 up to, so indicating that it's everything up to 20 but not including 20 here, sort of thing. Sometimes people do, 10 to 19.9 and then 20 to 29.9. And that might be okay if all your data is rounded to 1 decimal place, that would be fine. But the problem is if your data is not rounded to 1 decimal place, anything that falls between 19.9 and 20 doesn't have a place to go. So you just need to be careful about that and make sure every value has a place to go. Okay, let's work through an example. The raw data given below shows the number of runs scored by a batsman in each innings throughout a cricket season. Organise the data into a grouped frequency table using a bin width of 10. Okay, so we want to sort of think about the scale of the numbers we're dealing with here. So the smallest number is definitely 1. There are no 3-digit numbers. The biggest number is 97. So if we're going to use bin width of 1, we're going to go from 0 to 9, 10 to 19, etc. You could go from 1 to 10, 11 to 20. It's not going to cause us issues at either end because there's no 0 in the data anywhere, and there's also no 100 in the data anywhere. So it's up to you which way you decide to do it. So this is number of runs, and then it'll be frequency. So I'm going to go with 0 to 9, which means 10 to 19. Okay. I think it's nicer to start your interval on the whole number if you can. So rather than doing, my other option would have been to go from 1 to 10 and then 11 to 20. I think generally speaking, conventionally, because if we did that, 1 to 10, 11 to 20, then on your scale you would actually have to label the 11 as the value and label 1 as your starting value, and it's just not quite as nice. Alright, let me get rid of that. Alright, I'm just going to pause the video while I complete the table. Okay, so I haven't fully completed it. I want to sort of talk through that, a few things to do with that together while we do it. The other thing is, okay, yes, 100's not an option here. The batsman could have scored 100 runs, but then you just add an extra category on. Then there would be 100 to 109. If you scored that's where you've got it. That's the decision you've got to make in, what's your biggest value, what's your smallest value, how you're going to choose to divide it up. This is a sort of place, there's a lot of places in data analysis where if you make mistakes here, the whole thing's going to go to pieces. So it's really important that you are careful and take your time. What you might choose to do, actually, and what is quite common, is you might actually add in a column for tallies and then have your frequency column. And what that lets you do is it adds in an extra step, but it's a bit harder to accidentally miss off a piece of data. Okay, so that way you just work your way through the list. 42 goes in this category, 18 goes in this category, 5 goes in this category. Cross them off as you do them so you don't accidentally count them twice. 97 goes in this category, 61 in here, 47 in here. This one. Okay, and then once you've done that, it's easy to work out the frequencies. Otherwise, what you have to do is, and again, I would cross them off every time because then it'll allow you to see if you've missed any at the end. If you're looking for all of those in the 0 to 9 category, you'd go through your list. Okay, there's 1, 2, 3, 4, 5, 6, 7. Hopefully that matches our tally. 1, 2, 3, 4, 5, 6, 7. Yeah, okay. So that's the other way you can do it. Rather than, if you don't include a tally column, that's fine. Between 10 to 19, okay, I've got 1, 2, 3, mistakes there, 4, 5. My tally says 6, this one, 6. Okay, but yeah, cross them off as you go, because otherwise, you'll do the tallies and you'll get to the end and you realise you never crossed that one off, and that means you can then adjust it. You should also then always do a check and make sure your frequencies add up to the total number of bits of data that you had. So let me just fill the rest of these in. I'm just going to use my tally. 3, 2, 3, 2, 2, 3, 0, 2. Let's add them up. 7 plus 6 is 13, 16, 18, 21, 23, 25, 28, 30. Check that you've got 30 bits of data. If it's nice and organized here, I can see that I've got 3 bits of data that way by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bits of data that way. Oops, 10. So 3 by 10 means there's 30 bits of data there. Okay, so we've got our frequency table, so we can then construct our histogram. So we want to, we're going to have, how many intervals have we got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, I've just also counted the grid paper, and there's 30 squares across. So I'm going to draw my axis right at the edge then. I wouldn't necessarily draw it at the edge, but I want to be able to use every horizontal square that I can. I might draw my horizontal axis a bit further up so I've got a bit of room to write above. I don't need a heartbeat because we're starting at 0, so the data's going to start right up at the edge there. We're going to label our axis, so this is going to be frequency. This is going to be number of runs. and I'm going to use 3 boxes for each group, so that's going to be 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. Okay, so, and then we need our frequency. So the biggest frequency is 7. So we can probably sort of count up in twos here. Let's go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we've got our scale for frequency and for runs, and then we're going to draw our histogram in. So the first bar between 0 and 10 is 7, has a height of 7. You know, you should use a ruler here, make sure it's a nice, precise, accurate. It's hard to rule on the computer screen here. Now, I automatically shaded that in. You don't have to shade it in. Sometimes when you've got grid paper, it helps so that your bars of your histogram don't get lost amidst the grid paper. You can shade it or do a different pattern or whatever it might be. The next bar is 6. And then we have 3, 2, 3, 2. We have 3, 2, 3, and 2. 3, 2, 3, 2. 2, 3. 2, 3. And that's going to be 0, 2. You can choose to colour the whole thing in or shade it, or you don't have to. And there we've got our completed histogram. Okay, part C here to finish off. I want to follow the steps which I've got outlined below. I'll scroll down there in a second, to create this histogram using our CAS. Okay. Generally speaking, I was going to say generally speaking, it's just as easy to do it by hand, but the sorting of the data is quite time consuming, so, you know, but equally it's a bit time consuming to enter the data into your CAS, so that's up to you. And you still ultimately need to draw the plot on paper. Okay, so let's just have a look at the instructions here. So the first thing I want to do is I want to start a new document. So in Further Maths I tend to work in document mode rather than the scratchpad, whereas in all my other subjects I tend to work in the scratchpad, but Further Maths, in the data module, we need the data option, so we need to work in documents. I strongly advocate starting a new document. Okay, if it says, do you want to save your old document? No, you do not need to go back to the document you used yesterday. You don't need it. I've had some students get to the end of the year and their CAS is running so incredibly slowly, and then I realise it's running really slowly because they've got thousands of documents saved, because every time it says, do you want to save the document, they've said yes. So they've got, you know, reams and reams of these useless documents from problems they did back in, you know, at the start of the year that are taking up space. So start a new document every time. That will mean that you don't have any variables stored. There's nothing potentially going to confuse things. Everything's nice and clean and fresh. So we're going to start a new document. So it's either choosing one from the home screen like I did, or Control N at any time to start a new document. I'm going to choose number 4 for lists and spreadsheets, and we need to enter our data in first. So it's univariate data. We're just going to have one column of data. So my data is going to go in the first column, and it's always good practice with your CAS to name your data column. So in this case, our data is about runs, and it goes right in that very top grayed out box next to the letter A. I'm going to call it runs. When you name the data, it makes it much easier to access it when you are then wanting to do other things with it, because you can simply refer to the variable name, and I'll show you a quick way to get that. The other thing I want to say to you is, please don't call a column of data a single letter. Don't call it X, okay? Because if you then open a calculator page and try to solve an equation with X in it, it will create all sorts of problems because your CAS thinks X is a list of data and you are now trying to use it as an unknown, okay? It's not going to be such an issue if you are vigilant about always starting a new document. then those defined things won't hang over and cause problems for you down the track. But it's just a really good habit. Even if I talk about this in other videos, I talk about it in videos later on in the topic. Sometimes I just call it XV for X variable. But it just means it's not a single letter. So when I'm working with algebraic things, it won't create problems for me. Okay, so I've named my column for runs, and then I just need to enter my data in here. And I'm just going to pause the video while I do that. Okay, so I've scrolled back up in the notes here just so I could see the data while I've entered it in. I'm confirming that when I've typed in my last piece of data, I'm in row 30 of the spreadsheet. That's a nice little check for me because I know there were 30 pieces of data. I also really took my time in entering it in. This is one of those places, if you make a mistake in entering in the data in, an exam, and you get therefore an incorrect plot and you draw it incorrectly on the exam, there's no way of someone working out which bit of data you entered incorrectly and how you entered incorrectly and how that then resulted in the plot. Your answer's just going to be wrong. So really invest the time in putting the data in accurately so that then you know that what's going to come out of it's correct. Okay, so we've got our data. Now we need another page. There's a separate page for actually doing plots. So we enter the data in a lists and spreadsheets page, and then we need to press Control-I to get a data and statistics page. So that's number 5. So Control-I is insert page, and then I've chosen number 5 for a data and statistics page. So now what you have here is a random series of dots, each of which corresponds to one of the data values that I typed into the lists and spreadsheets. But they're just meaninglessly, they've just been thrown on the screen here. So first thing I want to do is where you can see at the top left, on the left hand side and at the bottom, it says click to add variable. Now we've only got one variable here, so we can't add 2 variables, one to the horizontal axis and one to the vertical axis. So if I've only got one variable, it's always going to go on the horizontal axis. So I'm going to click here in this grey area. So on your handheld, that is using the touchpad to move the cursor into the grey area and then clicking in the middle of the touchpad. And then it will bring up a list of the variables that I have defined. Now if I started a new document at the beginning of this, I've only defined one variable, it's called runs, and I can use that. If, however, I didn't start a new document and I've got, 14 tabs open and I've done 3 other plots, I'll have a whole list of variables here that might be hard to navigate. It's another advantage of starting a new document frequently. Okay, so now it's ordered that data into a dot plot on the bottom axis. We'll talk about dot plots in a future video. So now what I want to do is, we're up to step 7 here, we want to change the dot plot to a histogram by pressing menu 1, 3. Okay, so menu 1 for plot type, 3 we want a histogram. Okay, and it will draw a histogram, but you can see here that it's using intervals of width 5, so it doesn't match the plot that we drew. Okay, so with the cursor in the plot area, by that I mean this sort of white area and the blue area here, so mainly the white area, so not in the grey region, but in the white region. So with the cursor in the plot area, press Control Menu, so that's a right click, so I'm going to have to do that as a right click on the computer. So right click, and that brings up what we call the contextual menu, so things that are relevant to what's happening on screen here. And what we can see is that we've got number 5 at the bin settings, so we want to edit the bin settings, and we want there to be an equal bin width. Okay, so sometimes your CAS gives a variable bin width, but we want it to be equal, and we want that width to be 10. I also want the alignment to be at 0. It's already at 0, but that means I want my first bar to start at 0. Sometimes the CAS chooses a strange alignment, and it's important to know how to adjust that. Okay. And now it's going to do that. Now, because it made a wider bin width, it now has higher frequencies, and it hasn't, I don't know why it doesn't do this, but it hasn't scaled the vertical axis so that we can actually see what's happening. So what we want to do is adjust that, and the quickest way to do that, this is the only time I advocate using zoom, is to do menu 5 for Windows Zoom, and then choose 2 for zoom data. And it will zoom the screen. Now that what you should now see is if you hover over a bar, you'll see that the bar goes from 70 to 80. So interestingly here, the square bracket next to the number 70 says that 70 is included in this bar, and the round bracket next to 80 says that 80 is not included. So it's everything up to 80 but not including 80 is in this bar, and right down to 70, and it does include 70. And it says there are 3 data points in this bar. And we can see that information for each bar just by hovering over it, or if you click on it you'll see the same thing as well. Yes, because it's a bit harder to hover with the handheld sometimes. Okay, so that's our completed histogram. It should match the histogram that we've drawn on the paper, provided we entered our data incorrectly. Data incorrectly. Okay, so describing the distribution from the histogram or frequency table. So quite often you'll be asked to describe the distribution, and there are a number of things you're going to need to refer to if you're describing a histogram or a frequency table. First is shape and outliers. So you need to be able to describe the shape and the outliers. I'll talk about that in a minute. Center and spread. Those are the 3 things that we want to make reference to. So shape and outliers is the shape of the distribution can either be symmetric, positively skewed, or negatively skewed. Now, I find some students get a bit caught up in if something's not perfectly symmetric, they don't call it symmetric. It doesn't have to be exactly perfectly 100% symmetric. That's not the reality of data. But if the shape is approximately symmetric, you would describe it as being so. If it is positively skewed or negatively skewed, you would describe it as being so. So to me, these are counterintuitive words. I always remember these by thinking it's the opposite of what I think it should be. Now this might make perfect sense to you, but what we have when it's positive skew, it's when most of the data is on the left-hand side. Now to me, the left-hand side means negative, and that should be negative skew. So the word positive skew doesn't make sense to me. I had a very nice colleague once describe it to me as a good way to remember it is that the data has been pushed from the positive side, okay, to create positive skew. The data has been pushed from the negative side to create negative skew. If it hasn't been pushed at all, it's nice and symmetric, okay? So you want to talk about skew. If there is skew, you want to note that it's symmetric if it's symmetric. Sometimes you might also, it might be none of those things. You might get a fairly flat distribution, in which case I would describe it as that. Okay. The data might also display outliers. Now, outliers are values that are distinctly different compared to the majority of the data. Down the track, we'll look at technically how do we identify something as being an outlier. At this point, we're really just looking at, when looking at a histogram, we're really just looking at, is there a value that's, a bit separate to the rest of things? So this shape of this first plot here, we might describe that as positively skewed with an outlier. So the outlier statement is part of the shape, okay? This we might describe as negatively skewed with an outlier. This one we would describe as symmetric. Interestingly, if there was, and this is where it's important to mention an outlier, let's say we had that. Now some students will go, oh, well, that's positively skewed. But actually, I would say it's actually pretty symmetric, except there's 2 outliers, or a couple of outliers. Okay, so I would describe this as symmetric with outliers. Okay, approximately symmetric with outliers. So shape and outliers definitely needs to be mentioned when you're asked to describe a distribution. The next thing we need to mention is the center. And these will be true of other kinds of plots too. When we talk about box plots and things down the track, we'll need to talk about the shape, the center, and the spread. Okay. When we have a histogram, the center is going to be measured by the median. And we're going to need to sort of do a bit of calculation to think about the median. Okay, so the median is the middle data value. So it's not possible to work out the exact median in a histogram if you've just got the histogram without the data, but you can still approximate it. So for example here, what we're looking at is, okay, there's no reason why I should have drawn it to the right of this box. I'll talk about that in a minute. There's 8 bits of data in here in this category. There is a further 12 bits here. There is a further 10 here, 6 here, and 2 more here. So in total, that is 20, 30, 38 pieces of data. So if we've got 38 pieces of data, this means that the middle is technically, there's an even number of pieces of data, the middle is at the 19.5 piece of data. You add 1 to your total number and divide by 2. Okay, so 39 on 2 is 19.5. So somewhere between the 19th and 20th piece of data. Now, this diagram has drawn the median to the right of that bar because, okay, the 20th piece of data, there's 8 bits of data in there plus 12 bits of data in there. That means there's 20 bits of data between here and here. So because 19.5 is very close to 20, the line for the median has been drawn close to the edge of that bar. However, there's nothing to say that the 12 bits of data that are between 25 and 30 could be 25, 25, 25, 25, 26, 25, 26. Do you know what I mean? So the 20th bit of data could be 26, in which case the median might be 26 or it might be 25. So, but regardless, the 19.5 piece of data doesn't fall in this bar. That's only got 8 bits of data. It does fall in this bar. Okay, so if we add up cumulative total, 8 here and 12 here, which means there is 20 bits of data from here back. Okay, if there's another 10 here, that would mean there's 30 bits of data from there back. So if the median had been the 32nd piece of data, it would be somewhere in that bar. Okay, so we don't know the actual median value. We know the median interval, or the interval within which the median lies. So you need to be careful about how you describe that. You would just say that the median number of cars is between 25 and 30. And then we need to talk about spread. Now, the only measure of spread we have here is range, and actually it's not even particularly accurate. So range is the maximum value minus the minimum value, and here we're making the assumption that the maximum value is 45, but there might not be a data value equal to 45. The highest value might actually be 42. So we don't know that, but we make that assumption, and the minimum value is 20, and so therefore the range is 25. 45 minus 20 is the range. So it just gives us a sense, though. It's not actually the perfect measure of the range, but it gives us a sense of how spread out the data is. So in describing the distribution of our cars above, this would be what I would write if I was asked to describe the distribution. The number of cars that passed through an intersection at each cycle of traffic lights was recorded. So same as we talked about with the bar chart, give some context. What's the data being collected? How is it collected? How many bits of data, which will be the next sentence. 38 traffic light cycles were observed. The distribution of the data was found to have a slight positive skew. I think you could probably also argue that it's approximately symmetric. In this case, it's not really clear-cut, with no outliers. The centre of the distribution, if there's no outliers, you probably don't need to say that, but if there are outliers, you definitely need to mention them. The centre of the distribution, the median, lies between 25 to 35 cars per cycle. So you do need to clarify what measure of centre you're using. So you probably just say the median of the distribution lies between 25 and 30. But if you're going to talk about the centre of the distribution, you need to be clear that that's median as opposed to mean. The median lies between 25 to 30 cars per cycle. And this is also the modal interval. That means the most common. Mode is the most common. The spread of the distribution, so mode is another measure of centre, median, mode and mean. So we can talk about both mode and median here, so it'd be worth mentioning both. The spread of the distribution, as indicated by the range, is 25 cars. Okay, so reference to context about the data, how many bits of data were collected, shape and mention of any outliers, centre and spread. Okay, so to finish off, some examples here. Describe the shape of each of the following distributions, making mention of any outliers. So this first one, I would say that that's approximately symmetric. Don't see any outliers, so no need to mention them. Approximately symmetrical. This one, I would say there is negative skew. Negatively skewed, again, no outliers. This one I would say is approximately symmetric, but it's actually also quite flat. Okay, so I would probably say it's approximately symmetrical, sorry. Or I would refer to it being quite flat. And here we have positively skewed. Because yes, whilst this shape is symmetric, it's very different to something that's shaped like this. When I think about an approximately symmetrical distribution, I'm thinking of a roughly bell-shaped distribution, whereas this one's quite different to that, so I would be wanting to mention that. Okay, final question here. The histogram opposite shows the marks obtained by a group of Year 9 students on a history exam. How many students sat the exam? Okay, so we need to work out the total frequency. So we can see that there are 20 students in that group, another 40 in that group, another 50 in that group, another 20 in that group, 20 and 30. So if we add up, 20 plus 40 is 60, plus 50 is 110, plus 20 is 130, plus 20 is 150, plus 30 is 180. So there's 180 students who sat the exam. Within which mark range was the modal mark? So that is the most common mark. So the most common mark, actually, this is not possible to answer. The question should really be which mark range is the which is the modal mark range? Which is the modal mark range? That is the most common mark range, and that is from 60 to 70 marks. The reason I make that clarification is because, again, we don't know what the actual data values are in this category. Perhaps these 20 bits of data in between 40 and 50, perhaps they're all 42. Perhaps we've got, 18, let's say 18 bits of data that are 42. Whereas between the 60 and 70, okay, we've got 50 bits of data, but maybe we've got 10 bits of data that are 61, and we've got another 10 bits of data that are 62, and we've got another 10 bits of data that are 63, and so actually the most common value is 42, but it's just, so it's the most common category, I guess, the most common interval. So within which mark range, within which, so it's just which is the modal mark range, question mark. Within which mark range was the median mark? Now we can say definitively that the median fits within a particular category, okay? The median is going to be a number within that range, whereas we can't actually say the mode will definitely be a number between 60 and 70. It's just the modal group. So within which mark range was the median mark? Okay, sorry, so I needed these again. So we said 180 students sat the exam. So the median is going to be add 1 to it and divide it by 2. Okay, so half of 180 is 90, so it's going to be 90.5. So it's a 90.5th value. So we've got to work out where that is. So there's 20 data values here. There's another 40 data values here, which means from there back there is 60 data values. We're interested in where's the 90.5th one. Then there's another 50 data values there. So 20 plus 40, so there's only 60 data values back here, but then there's 110 data values back here. So the 90.5th data value must be somewhere in there. So again, that's also between 60 and 70 marks. And then if the pass mark was 60, how many students passed the exam? Okay, so if the pass mark was 60, so there, we want to know how many are up here. So there's 50 students in that group, plus 20 in that group, plus 20 in that group, plus 30 in that group. So that is 120 students passed the exam. What percentage of students obtained a mark less than 70? So that's right, 120 students. What percentage of students obtained a mark less than 70? Okay, so 70 is here. There were 110 students who got a mark less than 70. So as a percentage, that's 110 students out of the total of 180 students times by 100% to convert it to a percentage. And let's insert a calculator page so we can work that out. So 110 divided by 180 times by 100 is, I'm going to say, approximately 61%. Let's go with to the nearest percent. So again, if you need to round off an answer, the question must tell you to what level of accuracy to round it. If it said to 1 decimal place, 61.1%. Okay. Alright, so the work on histograms is in exercise 1C.